Hello, we are continuing on with our rotational 5.0 module, and we're now at centripetal force, which carries over from centripetal acceleration. So again, centripetal acceleration is radial, it's along the radius, and essentially what a centripetal force is a result of the centripetal acceleration. If force is equal to mass times acceleration, and mv squared divided by r is that interpretation of that force, then that force, which is the result of the centripetal acceleration, is the centripetal force. So if the acceleration, since the centripetal acceleration is directed towards the center, that means the net force acting on the object is also acting towards the center. Okay? So, again, since we're going to be moving into force diagrams, and we're going to be essentially summing up those forces and setting them equal to mass times acceleration, as we always have done. But this is going to be equal to mv squared over r. Okay? So here is what we're going to be doing. We're going to be establishing a coordinate system and drawing our force diagrams. We're going to then be summing the forces up in the x direction and y direction, and then setting them equal to mass times acceleration. But some of those accelerations may be a centripetal acceleration. Okay? So let's talk about it. So let's do a problem here, and it'll make sense. Suppose you have a person who is spinning a hammer. They're doing a hammer throw, where they're spinning a ball that is 7.35 kilograms. Whew, that's like 15, 16 pounds. At the end of a chain, which is 1.2 meters. And they're spinning it up to a rate of 29 meters per second. Okay? They want to know what the tension in that string is going to be. Okay? So let's go ahead and let's draw our little force diagram based on this picture right here. Okay? So the ball is over here. We're going to draw our coordinate system. This is going to be positive x. This is going to be positive y. This is going to be negative x. Make sure that looks like y, and this will be the negative y direction. So that's our coordinate system. We're doing a force diagram on the ball. Okay, so the ball is right here. We're going to have a force, the mass times gravity force, acting down on it in the negative y direction, so that's going to be a negative mg. There is a tension force pulling it to the center of the circle. Okay. And so we could say this, it looks like it's moving in and out of the page. The velocity is going to be in and out of the page. Okay. And that means the velocity is moving towards us, but that also means that it's accelerating to the right. So let's use black here. Computer is running a little bit slow right now. Sorry, my computer is running a little bit slow. I'm going to delete that. But I'm going to draw the velocity vector. The velocity vector looks like from this picture it's coming out at us. The velocity is in the positive z direction. It's kind of hard to see. but the acceleration, which is a centripetal acceleration, is going to be towards the center of that circle. That'll be in the positive x direction. Okay, it'll also be in the direction of that tension, which we're going to call a positive t. Okay, well, let's sum the forces in the x and y direction. So sum the forces in the x direction, and this is really the only one that we care about, because we want to know what the tension on the string is, and that's only an x direction force. But let's sum the forces in both directions. So the forces in the x direction is going to just be that positive t, and that's going to be equal to a positive x direction mass times centripetal acceleration in this case. Okay. In the y direction, which I'll sum it in the y direction, you're going to have a force in the y direction. And this might not make any sense, but it's got a negative mg force down, right? And I should make that red. So there's an negative mg force, okay? But when we set that equal to mass times acceleration in the y direction, that acceleration is 0, okay? It's not falling down at all. It's only moving in and out of the page, and it's only accelerating to the right. So essentially what this is saying is that basically that gravitational force is not affecting its motion whatsoever. So this is kind of a unique case when the actual forces in the y direction is not actually mattering. So in this case, the tension force, which is pointed to the right, is equal to mass times the velocity squared over the radius. Okay, I'm going to use a capital R for the radius. So the tension in this string, which is what we're being asked to solve, is going to be equal to 7.3 kilograms times the velocity, which is 29 meters per second. And we're going to square this number right here. And then we're going to divide it by the radius, which is a 1.2 meter chain. Okay, so we're going to multiply that all out. We're going to do 29, and then we're going to square that 29. We're going to multiply that by 7.3, and we're going to divide that by 1.2 equals. So the tension in that string, and I'm just going to verify this is 29 that we squared. We're going to divide that by 1.2 equals, and we're going to multiply that by 7.3. So it looks like the tension in this string is going to, in this rope or whatever it is going to be 5,116. Okay, so that's going to be 5,116.08 newtons. Okay. All right. That's roughly like 1,000 pounds, right? You take this number, well, it might be a little bit more. If we divided this by 9.8, that's what it'll feel like in kilograms times 2.2 equals, so 1,148 pounds. That's like swinging a car at that point. I don't know if that's possible for a person to do that. I don't feel like this problem is very realistic. But that's the problems that we were given. There we go. Let's go on and do another problem. Okay, similar problem, but this time we're gonna have an angle to it. Okay. So suppose a hunter has 1 kilogram buck, and is making a horizontal circle over his head at 1 meter. And if the vine breaks at a tension of 200 newtons, what's the maximum angular speed at which we could swing the rock? Okay, so I'm going to go through an explanation. So in this problem, when he's swinging it, what they're saying is it's not going to be perfectly horizontal, which makes sense to me, because when we look up here, if we were swinging this and it was perfectly horizontal, then that would basically saying that it might as well be weightless. It almost has no weight. And the only way that's possible is if it is not dipping down below that axis, which I feel like even on the small scale, it couldn't be perfectly horizontal. Okay, so that doesn't seem realistic to me. But what does kind of matter is this. In this problem, they basically say the vine might break at 200 newtons, and they want to know what is the speed at which it will actually be able to spin at before it actually breaks. And they want to know it in terms of omega. So what they're doing is they're doing a force diagram right here, but they're also adding an angle to it. So since the rock is slightly below the horizontal, that tension string is going to be pointing up above the horizontal, which means that tension is going to be pointing radially to the left, and also it's accelerating to the left. So this is a negative t cosine of theta minus mv squared over r. But the upward component of this tension is going to be pointing up, t sine of theta, minus the weight of the rock, which is down. And since it's not accelerating in that in that y direction, okay, then that t sine of theta minus mg is going to be equal to 0. So then they go on to say here that t sine of theta equals mg equals a 0. So I'm going to mark this up. So one interpretation of the tension in the rope is going to be that t equals mg over the sine of theta. Okay. And then if we take that and we plug that into here, so I'm going to do this off to the side, right over here, that y direction motion is going to be t equals mg over the sine of theta. That comes from the y direction force diagram. The x direction force diagram over here, it gives you it's negative t cosine of theta mv squared over r minus mv squared over r, but this is going to be, if you take out that negative from both sides, multiply through by negatives, you get this as the interpretation for the x direction. Let me get rid of that little dash there. Okay. So there's a couple problems here. Well, not really problems, but let's use this right here. We know what t is. We know what m. Let's use this. This is the only equation that has v squared in it, and we're going to use that to find omega in revolutions. So let's do that. We're going to multiply both sides by r and divide both sides by m. So we're going to get r times t cosine of theta divided by m, and that's equal to v squared, right? And while we're here, let's actually make a relationship. V is going to be equal to 2 pi r times omega revolutions. So v squared is going to be equal to 2 pi r squared omega revolutions squared. So this is going to be 2 pi r squared. So actually omega revolutions. And we're going to make that omega revolutions squared as well. Okay? So let's do a couple things here. Let's go ahead and figure out what this 2 pi, so this is going to be 2 pi, actually let's rewrite this so it makes a little bit more sense. 2 pi cosine of theta, relating this to this, 2 pi cosine of theta over m, and that's going to be equal to 2 pi r squared. So 2 pi squared times r squared, omega revolutions squared. Okay, it's a lot. That r is going to cancel out with that. Let's bring this 2 pi squared on the bottom here. 2 cosine of theta divided by, well, let's figure out what 2 pi squared is. Let's take 2 times pi equals, so 6.28, and let's square it. So 39.478. So 2 pi squared is 39.478. We're going to bring that on the bottom over here. So that's 2 pi squares. And then we're also going to divide by the r, too. So we basically divided both sides by that 2 pi squared r and brought it on the bottom over here. And that's equal to our omega revolutions. Okay? And squared. Okay? So let's put in our numbers. This is going to be 200 newtons. This is going to be the cosine of theta over this. We're putting in what we know, 39.478 times 1 meter. We're going to square root all that to set it equal to omega revolutions. Here's the problem, though. We don't know what theta is. So what we could do is we could get that theta from right here. Sorry, I wrote some things just to plan that during a little break I had. So we could get that from over here, and I'll show you what I mean. So with the y direction equation right here, the y direction equation right here, we have t equals mg sine of theta. We know what t is, we know what m is, and we know what g is. So if we multiply both sides by theta and divided both sides by t, we could actually figure out what theta is. So if we take the inverse sine of both sides of mg over t, well, that theta is going to be equal to it was 1 kilogram times 9.8. We're going to divide that by the 200 Newton tension force. And what we're going to do is take the inverse sine of that, which is going to give us about 2.81 degrees. Okay. Move this down a little bit here. Okay, so now we know what this angle theta is. That angle theta, which I'm just going to write that in right here, is 2.81 degrees. I'm a big fan of letting the equations tell you what you do. So now let's figure out what this whole thing is right there. So that's going to be 2.81. We're going to take the cosine of that, which it's about 1, times 200. Now we're going to divide that by 39.478 times 1 meter. So divide that by 39.478 equals 5.06. Now we're going to take the square root of that. So now we know that is 2.249. 2.249 revolutions per second. Okay? But we need our answer in revolutions per minute. I think that's what the problem was asking for. So we're going to then multiply both sides of this by 60. So we're going to divide this, multiply this by 60 seconds and divide it by 1 minute. And so omega revolutions is going to be equal to, we're going to multiply this by 60 seconds, which is about 135, right? It's 134.97. revolutions per minute. And so, as you can see, that's the reason why this problem is more realistic. In this other problem, they're basically telling us this person's spinning it at such that it doesn't drop at all below that horizontal, which is impossible because this person would have to pull it with a force of, I think we figured it out, it was like 1,140 something Newton pounds, which is impossible. It has to drop a little bit below the horizontal. But now you know how to do both types of problems, okay? Oops, gotta be careful when I'm scrolling. So now let's do another problem. And this problem is really similar to the person spinning the ball problem in the very first part without an angle. But this is a car turning a corner, and they want to know what the maximum speed that a car can, that a 1,500 kilogram car can make turning left on a curved road with a radius of 50 meters on a level unbanked road without sliding. Okay, and so their basic. Let's start by doing a force diagram. Okay. And I think we're going to need more information because I think we need that static friction force. Okay. So here's the force diagram of a car, and I'm going to do this from the perspective of the car moving forward. I know in this picture we're looking on top of it. Well, I suppose we could do it that way. No, let's do it from where we're looking at it from the side. So let's say the car is driving away from us and we see them turning left. That's how I want to do the force diagram. Okay. So again, to the right is positive x. To the left is negative x. Up is positive y. Down is negative y. Okay, so the car is turning left. So the first thing we draw is the non-contact force due to gravity. That's going to be the negative mg direction. The road is holding up the car. So the car is going to be accelerating towards the center of that circle, and that's going to be a negative x direction centripetal acceleration. It's moving straight forward, so that's like a negative z velocity. That'll be a negative z velocity, but it's got a negative x direction centripetal acceleration. But basically, since tires work by static friction, what we could see is that that static friction force, which is going to be mu sub s times the normal force, which is going to be pointed to the left, has to be the thing that is keeping it on the road, right? A surface force is going to provide two forces. It's going to provide a normal force and a friction force. A force is perpendicular to the surface and another force that is parallel to the surface. Well, if the car is accelerating it has a centripetal acceleration to the left, well, there has to be a static friction force pushing it to the left. Okay? So let's sum the forces in the x direction. Okay? All right. In the x direction, we have a negative mu sub s times the normal force, and that's going to be equal to a negative m. So it's negative due to the negative centripetal acceleration times the centripetal acceleration. So this is going to be negative mu sub s times the normal force minus negative mv squared divided by the radius. In the y direction, we have a normal force pointing up, we have an mg force pointing down, and it is not going to be accelerating in the y direction at all. And this is f sub y right here. So that acceleration is going to be 0, so that means the whole thing is going to be equal to 0. So the normal force minus mg is going to be equal to 0. So the normal force is going to be equal to mg. We're going to replace the normal force over here with this. So I'm going to take this and I'm going to sneak it in right here. So negative mu sub s times mg equals negative mv squared divided by the radius. So the masses are going to cancel out. And what we're going to have left over here is this. Multiplying both, we're going to get rid of that negative and we're going to multiply both sides by r. R times mu s, that s looks weird, times g equals v squared. Now, in the problem, I don't recall them saying this, but I could see here in the notes that mu sub s is equal to 1 and that the radius is 50 meters. So when we solve for v right here, we're going to take that radius of 50 meters, we're going to multiply that by 1, and we're going to multiply that by 9.8. Running out of room, I'm going to move this over a little bit. By meters per second squared, and that's going to be our velocity. Okay, so solving for this, that's going to be 9.8 times 50 times 1, which is mu sub s, and we're going to take the square root of that. So that velocity of that car, the maximum speed it could go is 22.13 meters per second. Okay? Which is essentially what they found in their problem. So this is how they did it, which is very similar to how I did it. Okay? So there are a lot of problems on how to do these. You're going to have problems where they're on a flat road or a curved road, such that you're going to have a theta, and this is going to be an incline. You're also going to have problems where it's dipping down. You're going to have problems where it's coming up. These two problems are very similar, except you're going to have a different case here. Since it's on an incline road, basically your car is on an incline. This is one of those cases where it's a little bit more complicated, okay? Because you're going to have to take this as your origin. And let me actually rewrite this so I could show you how to do a problem where it's on an incline. And I'm just going to do it with variables. So just say there's a problem where car is on an incline, okay, and that incline is a theta right here, and the car is on incline. So essentially this is a car on an incline, and it's accelerating towards the center of the circle, okay? So that means the coordinate system for this is just like what we did with any problem where the object was on an incline, okay? This is the positive x direction. This is the negative x direction. This is the positive y direction. This is the negative y direction, okay? So when the car is on an incline, you're going to have the mg force pointed straight down, okay, which means this is going to be theta. If you don't remember this, we did this problem in forces, and it was the last module in forces. I think it was like 3.4. Okay, and so when we break up that mg force in terms of up and down and left and right, this part is going to be mg sine of theta pointed in the positive x direction. This is going to be positive, I should write it angled. This will be negative since it's pointing in the negative y direction, mg cosine of theta. Let me do something with that s, cosine of theta, and that will be pointing in the negative y direction. The normal force will be pointing up the track, and just like the last problem, okay, so yeah, it's kind of sliding down the ramp there, normal force up. Now, it's going to be trying to accelerate down the ramp, okay? So it's going to have a positive x direction acceleration. And it's going into, the car's coming out at us, so it's going to have a positive z direction velocity, right? But what's keeping it on the track? Well, yeah, basically you're going to have a static friction force keeping it from sliding down the track. And that static friction force, it has to balance out with this mg force, and that's centripetal acceleration. So this is going to be a negative x direction static friction force. Okay, that's what's holding it up the ramp. Okay. Let's sum our forces. Let's sum our forces in the y direction first. I always teach you guys, if you have friction, you probably should sum the forces in the y direction first. So here we're going to have normal force pointing up. We're going to have an mg force cosine of theta pointing down. And that's going to be equal to mass times acceleration in the y direction, which is 0. It's only accelerating in the positive x direction. So what we get is normal force minus mg cosine of theta is going to be equal to 0. So that normal force is going to be equal to mg cosine of theta. Okay? Sum the forces in the y direction. In the x direction, sorry. So in the x direction, we have that negative mu sub s times the normal force pointing in the negative x direction. In the positive x direction, we have an mg sine of theta, and that's going to be equal to mass times the centripetal acceleration. Okay, and that's in the positive x direction, so I didn't put anything there. We could take this normal force and plug it into here, in which case we'll get mu sub s mg cosine of theta plus mg sine of theta equals mv squared divided by r. As you can see, the little m's are going to cancel out. And you can multiply both sides by r. So I'm going to take this, I'm going to multiply it by r. I'm going to multiply the entire both sides by that. And set that equal to v squared. Okay. We could actually pull a g out at this point. So g times r, and this is going to be negative mu sub s times cosine of theta plus sine of theta equals v squared. But if you divide both, if we take the square root of both sides, you get this. It's a somewhat clean equation which relates all of those variables to v. Okay, so this is how to handle a car that's on an incline, right? Which is slightly different than this one, right? It has no angle, so much easier to do. The earlier one that we did. Okay. So let's talk about a case where instead of instead of going down right here. Actually, let's do this problem really quick because I think this is a pretty cool problem, and it's really simple. They already have the force diagram. You have a car driving along. It's got normal force up. mg force is going down, and it goes through a dip in the road, which means in this dip it's actually going to have a centripetal acceleration vector upwards, right? Because it's always directed towards the center of the circle. So when we sum the forces in our x direction here, we're going to have no forces in the x direction. Okay. So then we sum our forces in the y direction. It's going to have an interesting result. You're actually accelerating upwards when you dip down, which is kind of makes sense because that's what makes you feel lighter, sort of. You're almost in free fall. You got the centripetal acceleration. You have all these variables acting on you. So this is going to be like n minus mg, and that's going to be equal to a positive mv squared over r. Okay? So the normal force, when you add mg onto both sides, is not just holding up, it's not just holding up u, but it's also got to add to that, so the road also has to hold up your rate of turning or your centripetal acceleration. So when you go through a dip in the ground, the floor on the road actually has to hold up a lot more than just the weight of your car. It has to hold up the centripetal acceleration too. Okay, so the normal force in this case is going to be greater than the weight of the car when you're driving across a road that dips down. That's kind of that interpretation. In this question, though, they're asking you a similar question, but when you're going over a hump in the road. So suppose a skier is going over a hump in the road. At the top of the hill, what is the centripetal acceleration on the skier equal to? It's going to be equal to n plus mg, negative n plus mg, n or mg. So normally the normal force would just be holding up your weight. But when you go over a hump in the road, something interesting is going to happen. Okay, so we're going to write our little coordinate system. Here's our little skier. We don't need the x direction stuff, but mg is down. The normal force is up. But the center of the circle right here is below the skier. So the centripetal acceleration is in the negative y direction. So when you sum your forces in the y direction here, the normal force is minus mg is going to be equal to that centripetal force, mv squared over r. But the weird thing is, and that's going to be in the negative direction. So so when you multiply both sides, mv squared over r, and this is the negative direction, so we're going to multiply both sides by this negative to answer the question. So this is going to be negative n plus mg equals that centripetal force right here. So to answer this question, the answer is negative n plus mg. Okay, but take this original equation again and let's interpret something else. How much weight would the road be holding up? Is the normal force going to be equal to your weight, more than your weight, or less than the weight? Well, if we solve for the normal force, that means we're going to add mg onto the other side. So this shows the normal force is holding up the weight. But then you're subtracting off that centripetal acceleration. So when you go over a hump, the road doesn't have to hold up your entire weight. It has to hold up something less than your weight. So the normal force is going to be less than mg. Okay. So that's kind of interesting. So in this last question, they're saying this. Suppose you're in a roller coaster with a bucket of water, which I don't know who makes up these questions. I've seen this problem better off with a hat on the person's head, and they basically ask what's the minimum speed that you should be going to so that the water doesn't fall out. In other words, if you had a hat on your head and you're going in a loop right here, what's the minimum speed? What's the minimum speed that you need to go such that your hat doesn't fall out? Okay, so again, we're going to do a force diagram. Your mg is going to be pointing in the negative y direction. But now the normal force is also going to be pointing in the negative y direction. And you're going to be accelerating in the negative y direction. So everything is going in the negative y direction. So when you sum your forces in the y direction, you're going to have negative n minus mg equals negative mv squared divided by r. So multiplying through by a negative, you get this. And what we could say is this: we want to make it sure that we're able to just barely get over that hump. We want to just barely get over that hump. So if they're going too fast or really fast, the normal force is going to be acting on them. But if we want to kind of barely get over the hump such that the normal force kind of disappears. So in other words, we could actually say this. We're going to redraw this force diagram so that we could interpret it where the object is just barely getting over that hump. So here's our little quick force diagram. Going to wait for it to catch up. So that mg is acting on it like it always does, but this time the normal force, basically the roller coaster just barely makes it over. So that we could actually say this: the normal force at that instance doesn't exist. Now they're not going to fall off it. They're going to continue moving to the left, right? They're going to continue moving to the left with a negative x direction velocity in both cases. But this velocity on the left-hand side is much bigger than this velocity, because if this is big enough, the normal force is going to have to work on it to keep pushing it down. But at the moment where it's just about to fall off, that's when you're having that minimum velocity just to barely make it through. So what this means is mg is going to be equal to negative times our mass times our centripetal acceleration, which is v squared divided by r. So that mass is going to cancel out, multiply through by a negative 2. So we're going to get v squared divided by r. And so r times g is equal to v squared. So the square root of r times g is equal to v. So that's the minimum velocity that you need to cross this half without falling off the roller coaster. Or if you're swinging a pail of water overhead, that's the minimum velocity you need for the water to not dump out of the bucket. It would be whatever radius you're spinning it at times 9.8 square root. Okay, so I hope you enjoyed this video, and thank you for your time. Bye.